All right, here we are in chapter 3.6. This is the last section of this chapter and the last section of the semester. So this week we're going to be off a smidge for the week, so just kind of go with it. Today we have notes. Wednesday and Thursday will be lab. Friday review. Monday will be the quiz on 3.6, and then we'll have a couple days of review for the chapter test, and then a couple of days to review for the final exam. That is really the schedule through mid-January. So if you have any questions on that schedule, let me know. Check Skyward, check Schoology, make sure that you are aware, because we are again going to be off a little bit this next week or two as we finish up this chapter and finish up the semester. So this section is on momentum. Okay, and momentum is a property of an object that's related to its mass and velocity. Okay, so we have mass, we have velocity. From there, we should be able to figure out a lot of things. We know that mass is related to inertia. The more mass an object has, the more inertia. And velocity, if we have a velocity that is anything but zero, we know that that object is in motion. So momentum sometimes is referred to as inertia in motion. Okay. Key takeaway here is, because you have to be in motion, only moving objects have momentum. So if an object is at rest, it does not have momentum. Okay? Because velocity includes a direction, technically momentum includes direction as well. So if we look at the formula here, we've got momentum, units kilograms per meters times meters per second equals mass in kilograms times velocity in meters per second. So we've got our mass component, we've got our velocity component. Okay, when we are abbreviating for momentum, because m's already taken with mass, we can't use m anymore. So momentum is abbreviated P in the formula. So you get P equals mv. And you can quickly see through the formula that if our velocity was 0, it doesn't matter what the mass is, that object is not going to have momentum. So that again shows us this here, that only moving objects can have momentum. So let's do a practice problem together, and then one or two by yourselves. So what is the momentum of an 8-kilogram bowling ball running down the alley towards the pins at 2 meters per second? So first step, like always, is to identify our variables, P, M, and V. Remember, P is momentum, M is mass, V is velocity. So we can see here 8 kilograms for our mass. Velocity is 2 meters per second. And our momentum is question mark. If I come over to our formula triangle, I'm trying to find P. So P equals, M and V are next to each other, so I know to multiply. So now I can plug things in. 16. And our units are kilograms times meters per second. All right, here is one for you to try. Calculate the velocity of a 0.8 kilogram kitten with a forward momentum of 5 kilograms meters per second. Make sure to identify your variables and then plug things into the formula for what you are solving. All right, hopefully that made some sense to you. Simple momentum calculations, you will have to do that on the quiz coming up. Momentum. Okay. Two components that are involved in momentum again, mass and velocity. So momentum of an object can only change if the mass or the velocity change, or if both change. One thing that we also have is momentum can be transferred from one object to another. Okay, through a collision, when two objects collide, momentum can be transferred. Your speed's going to change when you hit that collision. And what this is this is called the law of conservation of momentum. The law of conservation of momentum says that if a group of objects exerts forces on each other, the total momentum of those objects doesn't have. So if we have momentum of object A and momentum of object B before a collision, after the collision, the total momentum of A and B is the same. Object A might be different, object B might be different, but that total momentum is the same. So let's look at what this is really doing. First off, our system must be defined. So in the earlier thing, we talked about a pin and a bowling ball. Okay, we got a bowling ball. Okay, and we have a bowling pin. Okay, not an artist by any means. It's a really bad bowling pin. But anyways, there's my system. My system's defined. Okay, I'm going to ignore the little bit of friction that is created during the collision. So when the bowling ball hits the bowling pin, a little bit of friction because you got two touching objects, we are going to ignore that. Okay, mathematically, we can determine the velocity of objects after collisions because we know that that momentum does not change. Okay, so if the momentum before equals the momentum after, okay, we've got the mass before times the velocity before equals the mass after times the velocity after. And really, you got to split this up into even a little bit more. So we have the mass of the bowling ball before times the velocity of the bowling ball before plus the mass of the pin before times the velocity of the pin before. So that's the momentum before. Okay. After, we have the same components. We've got the mass of the bowling ball times the velocity of the bowling ball plus the mass of the pin times the velocity of the pin. And that gives us the momentum after. So if we know what goes into the collision, okay, we can figure what goes out of the collision. So let's try this out together. So here we have our exact scenario. A person throws an 8-kilogram bowling ball down the alley at 2 meters per second. It hits a motionless pin with a mass of 1 kilogram and stops. What is the velocity of the pin after the collision? Okay, that is illustrating what's happening. So let's reset it. So we've got our bowling ball, we've got our pin. The bowling ball goes down the alley at 2 meters per second, hits the pin, the bowling ball stops, and the pin goes in motion. So we need to set this up. So best way to set it up is to have a table. We have our before and we have our after. Two objects that we have. We have the ball and we have our pin. So let's look at just the before. We've got momentum, mass, velocity, momentum, mass velocity. We don't know the momentum, but we know the mass of the bowling ball is 8 kilograms. We know the velocity of the bowling ball is 2 meters per second. So we can figure out what the momentum of that bowling ball is. That is 16 kilograms meters per second. We can do the same thing with the pin. Our pin has a mass of 1 kilogram and it's motionless, so the velocity is 0. So then the momentum of the pin is 0. It has no momentum, so we can cross that out. So what's the momentum of the entire system before? It is 16 kilograms meters per second. Okay, so the P of the system, the momentum of the system, is 16 kilograms per meter second. We know through the law of conservation that the 16 kilograms meters per second, that momentum before the collision, has to be the same as the momentum after. So then let's figure out what's going on. We've got our P, our M, our V of the bowling ball. The mass of the bowling ball hasn't changed. It's still 8 kilograms. But through the problem, we see that the motionless pin has a mass, okay, and the bowling ball, once it hits the pin, stops. So the velocity there is 0. So again, we have no momentum there. So now we just have to figure out what's going on here. So we know that if there's no momentum in the bowling ball, that all that momentum has to be in the pin. We know that the mass of the bowling ball hasn't changed. So now we can figure out, using P equals M times V, what our velocity is. Okay, and if we need to divided by our mass equals 16 meters per second. Remember, again, the formula for velocity would be P over M. So the velocity of the bowling ball is 16 meters per second. Okay. Highly suggest you guys set up a table similar to this when you do law of conservation of momentums. In our class, there's going to be something that stops. We're not going to have two objects going. We're going to make it simple for you. So here is one for you guys to try on your own. A person hits a 0.165 kilogram cue ball on a billiards table at 1 meter per second. It hits a motionless ball with a mass of 0.16 kilograms and stops. What is the velocity of the other ball after collision? Okay, so cue ball technically should be white. We're going to go with gray. Okay, is hit on a billiards table and hits another ball. Okay, the billiards ball, the cue ball, stops, okay, and all the momentum is transferred to the new ball. Figure out what the velocity of the ball is after the collision. All right, that is it for our lesson for today, momentum and then law of conservation of momentum. When you are done, you need to do the lab entry ticket and get everything set up for lab tomorrow. Let me know if you have any questions. Bye.